Hey everyone, welcome back, and today let's solve Leetcode problem 169 titled Majority Element. So I actually did solve this problem a few weeks ago on this channel, but I want to kind of revise this problem and explain it a little bit better because there is actually a very clever follow-up problem for this question. Because of course, the problem itself is quite simple, but the follow-up is what makes it kind of tricky. So let's just go ahead and dive straight into the problem statement. So we're given an array nums of size n, and we have to return the majority element. The majority element is the element that appears more than n½ times, where again n is the size of the input, and we may assume that the majority element always exists in the array. So that basically tells us that we don't have to look for any weird edge cases, and we're going to have one valid input and one valid solution for every single test case. So in example 1, we have the input array nums to be 3, 2, 3, and we would output 3 because 3, of course, is the majority element that has the highest frequency or number of occurrences in the input array nums, right? Of course, 3 has a frequency of 2, and the length of the input array nums is 3. Since 2 is greater than 3 divided by 2, we know that 3 is going to be the majority element. And in example 2, we have the nums input array to be 2, 2, 2, 2, 2, 1, 1, 1, 2. 2, and we would output 2 because 2 has a frequency of 4, which is greater than 7 divided by 2, where 7 is the length of the input array nums. So for the constraints, it's pretty simple. We know that n is going to be equal to the nums.length, or the length of the nums input array, and n is going to be not up to and including but not exceeding 5 times 10 to the power of 4, which essentially tells us that worst case we can have basically a big O of n runtime complexity. Otherwise, we'd probably get a TLE with exceeding amount of operations, because I think the most amount of operations you can have for a computer program in this case, in competitive programming especially, is going to be 10 to the power of 8 operations. So for the follow-up, it says that could you solve the problem in linear time and in constant space, which is what kind of makes this problem a little bit more interesting. But before we solve that, let's just go ahead and solve the problem regularly without actually solving this follow-up first. So how would we actually go about solving this problem regularly? We know very well that when we want to actually deal with the frequencies of different elements in Python, the best way to do that is just look at the frequency of each number using a counter. Right? Because the counter is basically a hash map that maps every single element in an iterable with its corresponding frequency or the number of occurrences. And I can do that in Python by simply setting a count to be equal to the counter and pass in my nums as my parameter, right? And I'm basically just getting the counter or the every single element mapped with its corresponding key value pair or its frequency and storing that hash map in the count variable. And to better visualize how this works, I'm just going to print out a count for you guys right now. And as you can see, if I were to submit this code, of course it wouldn't work, but I would get out a hash map, right? Basically mapping every single element of the iterable with its corresponding frequency, right? 3 has a frequency of 2, and so it would be mapped with 2. And 2, the key value 2 is going to be mapped with a key value pair of 1 because 2 has a frequency of 1 in the input array nums in this problem, or in this test case rather. So after we actually get the counter of nums, we simply want to loop through for I in the count, right? Basically looping through all the keys in the count. If count at I is actually equal, or not equal to, but greater than the length of nums divided by 2, we can simply return I, right? Basically the element that has a frequency or index I that's greater than the length of the nums divided by 2. And I could literally just submit this code right now and it would be accepted, it would be fine and great. And as you can see, it's accepted. But of course, we want to actually answer the follow-up, which is the hard part of this problem, where it says that we have to solve this problem in linear time and in constant space, or big O of one space. And so I'll give you guys a few seconds to kind of just go over that part in your head and think of a valid solution for the follow-up using this code that I have provided for you as a template. And yeah, I'll show you guys how I'd optimally solve this problem in a few seconds. Okay, so for such a problem, I think the correct algorithm name for this is the Boyer-Moore voting algorithm. Feel free to comment down below in the chat section if that's wrong, but I think that's the name of this algorithm, right? And essentially how this goes is first we'll initialize two variables, res and count, and they're going to both be initialized to 0, right? Essentially what this does is res, as we set it to 0, res is basically going to be storing the candidate for the majority element, and count is going to basically keep track of the frequency or vote count of each current candidate res for each iteration of the traversal of our input array nums, right? Hence why it's called the Boyer-Moore voting algorithm. I think so, right? Once we do that, we simply want to loop through, all the different values in the iterable nums, okay? So once we do that, now we actually have to check basically our base case for every iteration. If the current count for the current res, or the current element that we're looking at in this iteration, if that's actually equal to 0, basically it has a frequency of 0 for this iteration, we can set res to be equal to the new value nums at I, right? Again, if count reaches 0, it means that the current candidate res has lost all its votes, or frequency, and we need to select a new candidate. And we'll set res to that current element nums at I to be the new candidate, and that will mark the start of the counting votes for a new potential majority element, res, okay? So once we actually exit that base case, now we have to say, if nums at I, the current element that we're looking at in this iteration, if that's actually equal to the res, our current potential majority element, then we can increment its count, or vote, or frequency rather, by 1. If that's not the case, that's not the right element, and we have to decrement the count by 1 for future iterations. Again, what this does is, if the current element nums at I matches the current candidate res, or basically the potential majority element, we'll increment the count, and that basically means we're adding a vote for the current candidate. Otherwise, and what the else basically does is, if the current element nums at I is different from the candidate res, we'll decrement its corresponding count, and that basically means we're reducing a vote, implying a challenge to the current candidate's majority, okay? And eventually, outside of this for loop, we can just return res, which is the beauty of the Boyer-Moore algorithm, because we're guaranteed that the majority element, basically res, is going to have a frequency greater than n½ times. So even if all the other elements besides res are the same, it's still going to be less than the frequency of res. And the reason why we can just return res is, after the loop finishes, res is going to be storing the majority element, and the algorithm works because the majority element always wins more votes than the other elements combined, because it has a greater frequency than half of the length of the array. Okay, so for the time complexity, again, this is obviously going to be big O of n, where n is the number of elements in the nums list, and that's basically because the algorithm makes a single pass through the list, or basically it has a single iteration or traversal of the input array nums. And of course, the space complexity is going to be constant time, or big O of 1, because the algorithm really only uses a few variables, res and count, which are just integers that don't actually need any extra space, because they're not actually any extra data structures, and so no extra space is needed that grows with the input size. And this is a pretty efficient solution, basically leveraging the properties of the majority element, which does appear, again, more than n½ times, ensuring that it will always survive the vote count. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.